All right, welcome everyone. My name is Stefan Sommer. I am a member of the board of directors for NASCA, the Northern Arizona Climate Change Alliance, and you have joined the Northern Arizona Climate Change Alliance's speaker series called Climate Talks for Everyone. Today, we are very happy to have Dr. David Spence with us to talk about hydrogen, the hope and the hype. And let me just briefly introduce Dr. Spence. But before we get into that, so if you have questions as we go through the presentation today, please do put them into the chat and I will bring them forward to David as they arise. That way, since we have so many people in the room, people won't be speaking over each other. Okay, so please follow that protocol and I'll try to watch the chat carefully to bring your questions forward. Today we have Dr. David Spence. Dr. Spence is a physician who has been a pediatrician and general practitioner for 55 years. But for the last 20 years, he has also had interests in renewable energy and fuels. Today, we will hear about his interest in hydrogen and how hydrogen should be in our toolbox to help fix our existential climate crisis. And Dr. Spence, should I go ahead and pull up the PowerPoint?
Let's hold on that for for a minute. I want to start off by sharing a little bit of my story, how I came to be interested in hydrogen as an element in our periodic table. About 20 years ago, I attended a two-day workshop down in Phoenix put on by Roy McAllister, who was the head of the American Hydrogen Association at that time. And his credentials for putting on this workshop were the fact that he had converted a compact pickup gasoline internal combustion engine to run on hydrogen. He was an automotive engineer of sorts, and he had a compressed hydrogen fuel tank that he built himself, fed that into the engine of the small pickup, but he modified the engine so that it could burn gaseous hydrogen instead of liquid gasoline sprayed through a carburetor. In that workshop, he encouraged us participants to go home and start small, pick an internal combustion engine that we would like to convert, or another.
Apologize, everybody. It looks like David has frozen. Okay, he's back.
Yeah, we wanted to, I decided to convert a propane barbecue grill to use hydrogen instead of propane. And it indeed cooked the hamburgers as you would expect. The gaseous hydrogen burns with an invisible flame as opposed to a blue or yellow flame for propane. I also did the initial conversion of a gasoline-powered go-kart to burn hydrogen. That project, I realized I was in over my head, and I finally sold the go-kart to an NAU engineering student, and I lost track of that project. But through that webinar, I realized that hydrogen is no more dangerous as a fuel than gasoline. As a matter of fact, if gasoline were to come on the market now, EPA probably wouldn't approve it because it's too dangerous. But we've all learned how to live with gasoline, how to not smoke a cigarette when you're putting gasoline in your fuel tank. And the key thing about hydrogen when it's used as a fuel is that, keeping in mind that hydrogen is the lightest element in the periodic table. As a gas, it will go to the top of any enclosed space. So if you have a garage and a hydrogen powered vehicle, you want to have a peaked roof or a sloped roof. And at the very peak of your ceiling, you want to have an exhaust fan that will vent any hydrogen that has escaped, vent it out into the atmosphere where it will not be explosive. So over the years, I've kind of kept track of developments in hydrogen. And I want to start by reminding us that hydrogen is the most is the element in highest concentration in the universe. It comprises 72% of the mass of the universe. And if you count molecules, it's actually 90% of the molecules in the universe are hydrogen molecules. So it's ubiquitous. And I want to just give a brief review of our sun. The really source of all of our energy on Earth is the sun in one form or another. And the sun was formed, astronomers calculate, about 4.6 billion years ago. And as it got a concentrated massive core, nuclear fusion became possible in the core of the sun. And every second, our sun converts 600 million tons of hydrogen into helium through, as we know, the process of nuclear fusion. And in that process, you end up with 596 million tons of helium and 4 million tons of matter or mass are converted to energy. That's the famous equation that Einstein derived. Energy equals mass, the speed of light squared. I've never understood how Einstein came up with squaring the speed of light to get a calculation of how much energy is released when mass is changed to energy. But that's the equation. And every second, the sun forms the energy from 4 million tons of matter. Now, it takes about 10,000 to 100,000 years for that fusion in energy to exit the surface of the sun and make it on its way to Earth in 8 seconds. So our Earth is blessed with energy from the sun, as we all know. Now, here on Earth, our atmosphere, the air that circulates around the surface of the Earth, is 78% nitrogen, 21% oxygen, and 1% argon. So that makes 99% of the gases. The remaining 1% are called trace gases, and that includes carbon dioxide and other global warming gases, and hydrogen. Now, to put things in perspective, that 1% of our atmosphere that is made up of trace gases has the carbon dioxide and the hydrogen that we're talking about today. We've heard, and we all know, that our CO2 concentration is now around 420 parts per million. And on that same scale of parts per million, hydrogen makes up 1/2 of a part per million. So hydrogen is really a small component of our atmosphere, but it does make up a large percentage of the mass of our Earth, and it is in that equation we find hydrogen is locked into the molecules. Hydrogen is tightly bound to oxygen in water, H2O. It's tightly bound in carbohydrates, our food that we eat, has hydrogen tightly bound with carbon and oxygen and iron and other elements. Oil that our industrialization has relied on, and coal and natural gas all have hydrogen tightly bound with carbon. So the thing about hydrogen is that it is, as I mentioned, a light gas. It'll rise to the top of any enclosure that it's in. And if you have a kilogram of hydrogen gas, it will give you the energy equivalent of about 1 gallon of gasoline. So as we go through this talk, we're going to be considering how hydrogen can fuel our vehicles and power our economy. The hydrogen gas is at atmospheric pressure quite energy dilute. And the way to think about that is if you have a kilogram of hydrogen at atmospheric pressure, it would be in a volume equivalent to that of a cement mixing truck, the rotating tank on a cement truck that you see rumbling through your neighborhood. That would be 1 kilogram of hydrogen contained in the mixing tub at atmospheric pressure. So when we talk about hydrogen-powered vehicles, the hydrogen fuel is going to be compressed as a gas to something like 200 or 500 atmospheres pressure, or be in a liquefied state, which is called cryogenic. It has to be refrigerated, very cold to become a liquid. And in that state, you have a lot more hydrogen per unit volume, but there are energy consequences of turning the gaseous hydrogen into a cryogenic liquid. So let's, Stefan, let's go to the first slide, where if you can start sharing our slides. On the left side of this schematic diagram is a diagram of an electrolyzer. And basically, if you have a source of electricity, you can put it into an instrument, or let's call it a machine that will take the electricity. The power of the electricity will split water into oxygen, the component oxygen and hydrogen. And the oxygen comes off of the positive electrode in the water, and the hydrogen comes off the negative. You can use the oxygen for medical purposes, or you can buy it at an oxygen bar where they have flavored oxygen. At least this was popular a decade ago. I don't know if they still have oxygen bars, but oxygen is used as a welding gas. But for the most part, oxygen produced at an electrolyzer will probably be vented back into the air. The hydrogen can be collected and compressed into a tank, or like I say, refrigerated down to a liquid. So that's how you can produce hydrogen through an electrolyzer. In a moment, we'll come back to other ways to produce hydrogen in today's world. On the right side of this diagram is a schematic of a fuel cell. So this is the opposite reaction where you take hydrogen fuel, and this is depicted on the left side of that orange membrane. The hydrogen fuel from your fuel tank is allowed to interact with oxygen from the air coming on the right side, and that chemical reaction through the proton exchange membrane will create an electric current, which can power an electric motor, such as a vehicle, a car, or a bus. And these two instruments, if you will, an electrolyzer and a fuel cell, are the basis of what we're going to be talking about today. Okay, Stefan, let's go to the next slide. And I'm going to talk about the various ways that hydrogen can be produced in today's world. And I'm going to start with the most carbon dioxide polluting method, which is to take coal, and this is called black hydrogen. So black or brown hydrogen is from anthracite or lignite coal, and the coal is burned to do steam reformation. It produces hydrogen for sure, but it also produces carbon dioxide, which is our main greenhouse gas that we're trying to limit in our atmosphere. So black hydrogen is not good. Next is pink hydrogen. This is converted where you use nuclear power plant. And in this instance, the electricity from the nuclear power plant would run an electrolyzer, which we just discussed, and produce hydrogen and oxygen without any carbon dioxide as a byproduct. It does take water, and later on in our time this afternoon, we'll talk about how much water is required using an electrolyzer to get hydrogen. Next slide. Next is gray hydrogen. This is the most prevalent current technology. It's been present for the last 20 years, where they take natural gas and through a process called steam reformation, superheated steam, they convert natural gas into hydrogen. Okay, we've got our hydrogen, but we also have carbon dioxide. So this too is contributing to our current climate crisis. Blue hydrogen is where you have the same methane and the same reformation of methane into hydrogen, but here the carbon is captured and sequestered. And that's a whole topic of a whole nother hour's discussion on whether carbon capture and sequestration will be economically feasible and technologically feasible. They take the carbon dioxide that's produced from gray or blue hydrogen production and put it into underground caverns. It's also being used currently to inject into depleted oil and gas wells to have enhanced production of fossil fuels. So we have to be careful when Exxon or Conoco says they're going to inject the carbon dioxide back into the ground. Are they simply using it to get more oil and natural gas out to make their profits? Turquoise hydrogen is basically the same feedstock, methane, but they do instead of steam reformation, it's pyrolysis, which is more energy efficient. But it too produces carbon dioxide. Next. We come to green hydrogen, which is producing hydrogen from water using electricity. And if you were to hook up an electrolysis machine to the average electrical grid in the United States, where we have about 85 to 90% of our electricity in the grid comes from fossil fuel sources, then you're not producing green hydrogen. Green hydrogen, by definition, is using renewable electricity, such as wind, solar, geothermal, wave, or tidal energy, sources of electricity that don't put CO2 into the atmosphere, and using that green electricity to electrolyze water, and you get hydrogen and oxygen without any carbon dioxide. And that is the current thrust. The technology is available, although the electrolyzers, there's certainly a big effort going on to improve the efficiency of electrolyzers, to get an electrolyzer that doesn't require pure water, so that they could use treated wastewater or other forms of water instead of fresh water. I'm going to come to two theoretical sources of hydrogen production. Depicted here is yellow hydrogen, and it is an amazing process. And I'd like to give you a website reference if you'd like to look this up. What I'm about to tell you is pretty incredible. If you look up www.sunhydrogen.org, don't do it right now because I want you to hear my talk, but after we're done, Google sunhydrogen.org and you'll be able to read about this yellow hydrogen, what's termed yellow hydrogen. And it's a mouthful. I'm going to say it slowly for you. It uses photo, electro, synthetically active heterostructure. And you can abbreviate that with the initials PAH. And the reason this is still under development is it uses nanoparticles. And they take a billion or maybe 2 billion nanoparticles, build them into a unit that looks like a PV panel, a photovoltaic panel on people's roofs, or in a utility scale solar power plant. But this is a different kind of a panel. It will take sunlight on the front side, feed water into the interior of the panel, and off the back side comes hydrogen and oxygen. It does not convert the sun's energy into electricity. It somehow magically, if you will, using this nanoparticle technology, does a direct conversion of solar energy into splitting water. And I want to hasten to say that this is still in the experimental and developmental stage. They've proven it on a laboratory bench, but now they have to figure out, can it be commercialized? If it can be, it will be game-changing, and it's certainly something to keep our eyes on for the future. And finally, we have gold hydrogen. And I don't have a slide for this, but I want to um, tell you about this. It's called geologic hydrogen. And people have known about hydrogen seeps for a long time. In Turkey, there are the equivalent of an eternal flame, where hydrogen seeps out of the ground in certain locations on our globe. And the scientists think that fairy rings that are circular plant formations and a slight depression in the earth, that fairy rings are caused by these hydrogen seeps. And one classic way this was discovered in 1987 in the Mali nation in Africa, they, in a small village, they were drilling a water well. But instead of striking water, they came to a point in their drilling, I think they were a couple hundred feet down, and a gas started coming out of the borehole. They didn't know what it was, but one of the workmen who had a lighted cigarette leaned over the borehole, and the gas caught fire. He was burned. Fortunately, he survived. And the people realized, after consulting with some experts, that this was in fact hydrogen gas coming up from their water well. In fact, this village capped the well, and they've been able to use the hydrogen to power their village ever since. And there is considerable interest around the world in looking for places where geologic hydrogen might be available if we could find it. And the good news for the well drilling technology, if we turn from drilling for oil and natural gas, these well drillers could explore our Earth for hydrogen storage, hydrogen stored underground. The process has been elucidated by engineers and scientists. The hot magma in certain parts of the Earth, the hot magma will react with iron-containing rocks and water to create the hydrogen. And in certain geologic structures, the hydrogen might pool and be subject to extraction. The beauty of gold hydrogen is if it can be discovered, that it could well be a long-term self-renewing process and would not be contributing to global warming. So keep your ears open for geologic hydrogen and for photoelectrical chemical hydrogen, which we'll call yellow hydrogen. Now, we can turn off the slides, Stefan. And currently, industry in our country uses about 10 million metric tons. And by the way, a metric ton is 2,200 pounds in our English system. So roughly an English ton is 2,000 pounds, and a metric ton is 2,200 pounds. So they're on the order of a magnitude comparable metric and English tons. In our country, we use currently 10 million metric tons of gray hydrogen. This is used in industry to produce ammonia, ammonium fertilizer, and in refining industry, the oil refineries use gaseous hydrogen to refine the crude oil into gasoline, diesel, and other petroleum products. About 55% of that current hydrogen is used in refining, 35% in making ammonia fertilizer and methanol alcohol, 2% is used in metal refining, and then the remaining 10% is used in forklifts and standby power generation for telecommunication sites, and in a few buses and vehicles. Now, I am proud of the Biden administration for the progress that they're making with regard to hydrogen, and the 2 acts passed by Congress, the bilateral bipartisan infrastructure act, and the Inflation Reduction Act, both have a lot of money for hydrogen development in our country. And the government has published a 100-page document, and I've printed it out for my study. This 100-page document is called the U.S. National Clean Hydrogen Strategy and Roadmap. And as part of this roadmap and these 2 acts of Congress in 21 and in 22, they created a grant program called the Hydrogen Hub grant program. And Arizona did submit an application which was not funded. The 7 hydrogen hubs around the country are on both coasts and on the Gulf Coast and in the North Central. The purpose of these hydrogen hubs is to demonstrate how green hydrogen can be produced and then transported to sites where it will be utilized. And these demonstration grants each have about $1 billion for 4 years of operation. And they're going to demonstrate how hydrogen can be generated and used in our economy. The closest one to us is in California. They're going to use hydrogen from wind, solar, and biomass to put into public transport, into the port facilities, and heavy-duty trucking. So as these 7 grants, which are really well funded with $1 billion of federal money each, and each of the hubs has to provide a local match. So the estimate is a total of $40 billion of developmental work is going on through these hubs. And this roadmap that I just showed you has a goal of 10 million metric tons of green hydrogen by 2030. So we're just starting 2024 today. In the next 6 years, the government's goal is to have as much green hydrogen production in our economy as we have gray hydrogen now. And by 2040, the goal is to go up to 20 million metric tons, and by 2050, be at 50 million metric tons of green hydrogen in our country. Mm-hmm. Now, the hydrogen, one of the best uses of hydrogen today is in warehouses where they rely heavily on forklifts. And I'm going to use the forklift as a way to explain the advantages of hydrogen fuel cell powered vehicles over electric battery powered vehicles. And if you think about a forklift operation in a warehouse, the refueling time is critical. If a forklift has to be parked for 2 to 4 hours to recharge electric batteries, this would be an electric battery powered electric forklift. It'll have to sit idle, not lifting boxes, for 2 to 4 hours to recharge. Whereas a hydrogen fuel cell powered forklift can be refueled in 10 minutes, approximately the same length of time to refuel a gasoline vehicle.
Dr. Spence, there
Yes.
are a couple of questions that come in through the chat.
Sure, go ahead.
So one is about if we do end up producing enough green hydrogen, won't there need to be an infrastructure of pipelines to deliver it?
It's a good question. And yes, the mechanisms to deliver the hydrogen from where it can be produced to where it will be used can be a pipeline. And there's active research going on to see how much and the feasibility of using some of our natural gas pipeline distribution system. We have 200,000 miles of natural gas pipelines buried in our country. So it will take some retrofitting to allow hydrogen to be safely transported through pipelines. Some valves, some pumping stations would need to be retrofitted to be able to contain the hydrogen. The difference between hydrogen and natural gas is that hydrogen is much smaller. We'll find smaller holes to get through than natural gas. So there are pipeline possibilities. If you build a new hydrogen pipeline that's specific to transport hydrogen, yes. And I'll come at the end of my talk today to a blue sky aspiration for a pipeline here in our community. The other way to transport hydrogen is through a tanker truck. And this can be a pressurized tank or liquefied cryogenic hydrogen. And currently in California, there are some 60 hydrogen fueling stations up and down the interstate corridors in California. And these hydrogen fueling stations are predominantly supplied by a tanker truck that pulls up several times a day or maybe several times a week to refill the gaseous storage tanks with hydrogen. So yeah, it will need to be transported, and part of the Hydrogen Hub grants is to demonstrate what is feasible and what is economic. Is there another question?
Yes, well, there was one, but I think you're already in the process of answering that. If the 2030, 2040, and 2050 goals are met, what will they be able to power as a practical matter? Cars, planes, home heating, and I think you've started that with the forklift.
Right. I think if there's one take-home message from our discussion together today is that hydrogen, well, it's been around for a long time through the steam reformation process using natural gas feedstock. We've got a lot of experience on that, and most of that production activity goes on in one location. In other words, they have natural gas coming through the natural gas pipeline system, and at a particular location, they do steam reformation to make hydrogen, and then it's immediately at that same location turned into methanol or ammonia for fertilizer, or used in refining oil products, the oil refineries. So what we're at the beginning stages is figuring out how to produce hydrogen from all these new green electricity sources, the wind, the utility scale solar systems, the geothermal plants in Nevada and California and Wyoming, the wave and tidal energy projects that are being researched currently, and hydroelectric in the Northwest. There are times when the Columbia River hydro plants produce more electricity than the grid can accept. And so using that excess electricity to produce hydrogen from water by electrolysis, and then transporting that hydrogen to cities and farms where it could be used is really very much in the beginning stages. So here in 2024, we can expect a lot of development over the next 1 to 2 decades in how to produce and transport hydrogen. So it's an exciting time to be learning about hydrogen. So let me just give a little more description about what's involved in producing hydrogen using electrolysis. And if we could go to the slide that shows the global hydrogen or the global water consumption.
Yes, let me work on that.
Basically, one of the concerns you'll hear about hydrogen electrolysis is, well, how much water is it going to take? And if we're already in drought conditions, particularly in the Southwest, isn't this going to impact our scarce water supplies? And I have a slide here that shows the global water consumption, the large rectangle slide. Okay, this large rectangle is the breakdown of freshwater consumption around the world. And the bulk of the rectangle is the current global freshwater consumption. Off to the right, in the medium blue, is the current US freshwater consumption. And then below that, in the lighter blue, is what's used currently in the United States for agricultural irrigation. When you get down to the very bottom right corner is a projection for the year 2050, assuming that we and the rest of the world ramp up hydrogen production from using electrolysis. That little dark line at the bottom is the world's water consumption to produce hydrogen. And the little tiny end of the bar at the lower right corner is the United States water consumption for hydrogen production. So if you look at how much water is going to be consumed to produce hydrogen, yes, it does take 4 gallons of water to make 1 kilogram of hydrogen. And let's show the next slide with the bathtub. To put this into some units that you can more easily understand, pictured here is a bathtub full of 300 liters of water. That's a typical bathtub with the soap suds on the top. 300 liters of water put through an electrolysis unit would take a fuel cell truck 235 kilometers. So that much water, 300 liters, put through an electrolyzer with green electricity, would take a fuel cell truck, fuel cell powered delivery truck, 235 kilometers. If you took that same amount of water to produce a diesel, and here the diesel has to be produced from oil that's pumped out of the ground, refined in a refinery, that diesel truck would only go 141 kilometers. So this illustrates that while hydrogen electrolysis to produce hydrogen does use water, it uses less water than we're currently using to power our economy. All of the nuclear power stations have, and all of the coal-fired and natural gas electricity generating stations have big cooling towers. And these cooling towers consume water. And just to remind people, when Peabody coal was being mined on Black Mesa on the Navajo and Hopi reservations, there was a period of about 20 years when they sent a coal slurry from the reservations to Las Vegas, Laughlin, Nevada, to generate electricity for Los Angeles and Las Vegas and Phoenix. And that coal slurry took pristine aquifer water to transport the coal through the pipeline. So yes, hydrogen will take some water, but not as much water as we've been using in our fossil fueled economy. And in terms of the water, there really does need to be a new paradigm for how we look at water in our country. And this is a whole nother hour lecture, how to look at our water resources. But as we go forward in hydrogen production, the experts need to look at alternatives to pristine aquifer drinkable water. And an electrolyzer does require relatively pure water. They call it 99.9%. But you can get that from recycled wastewater, from desalinization of ocean water, and from other wastewater sources. So the people that are promoting the hydrogen economy need to look at using water other than our drinking water. Let's go to the next slide, Stefan, that shows the vehicles. So here we see some high school students using fuel cell cars in a high school competition. We see buses that are zero emission. These are fuel cell powered buses. You have a hydrogen tank on the top of the bus, or a series of hydrogen tanks, and a large fuel cell that takes the hydrogen from the fuel tanks, air, oxygen from the air, puts it through a fuel cell that generates electricity that drives the electric motors. And these fuel cell powered buses are on the road now. I think there are 80 fuel cell powered buses in our country. The automobiles pictured here, there are currently 3 manufacturers, Toyota, Honda, and one other car company that have fuel cell vehicles for sale in California. California has, I think the number is 16,000 fuel cell vehicles on the road, and there are 60 hydrogen fueling stations scattered in the metropolitan areas of California. Connecticut also has hydrogen fueling stations. So over time, hydrogen fueling stations may become available if there's a demand, and it's the classic chicken and the egg conundrum. How are people going to fuel cell vehicles? Where are they going to find the hydrogen? And how are we going to get hydrogen until there's a demand for the fuel? Next slide. Here's a architectural design of a hydrogen fueling station with solar panels above it. Now, truth be told, this number of photovoltaic panels would not generate enough hydrogen to fuel very many fuel cell vehicles. But the concept is depicted here of generating, using the sun's energy to generate hydrogen and then use it locally. You wouldn't have to transport it through a tank truck or through a pipeline if you can generate your hydrogen close to where it is going to be used. And one of the great things about hydrogen, and I'd like to leave you with this thought, is that hydrogen can be a great democratizing influence in our society, in our world society, much the way that cell phones have been democratizing. The developing countries of the world have skipped over the landlines and they've gone directly to cell phones. And so hydrogen, if you can develop it, if you can isolate hydrogen from water using the sun's energy, it becomes a democratizing energy system. Let's go to the next one. One of the things we need to solve in our developing renewable energy is how to store energy. As we know, the wind is inconsistent. There are days when the winds calm down to where the wind turbines don't turn. At night, your utility scale solar panels aren't going to be generating electricity. And we need storage of our energy to even out the availability for the grid. Battery storage is certainly being worked on very intensively by industry, and you know, Tesla has the Powerwall. You can purchase a battery backup system for your home photovoltaic panels and be off the grid if you choose to invest in a battery backup system. Pumped hydro is a system where you use your excess electricity during the day to drive an electric pump, electricity powered water pump to pump water up to an elevation, and then at night let the water flow back downhill, generating electricity through the night. Likewise, hydrogen can be stored when there's excess energy available, when the wind's blowing and the sun's shining, and it's more than the grid is able to utilize. Then your hydrogen produced by your electrolyzer can be pumped into a storage container, and there are basically 3 levels of storage. And you could think of it as hour-to-hour storage, day-to-day, and season-to-season. The hour-to-hour storage would be in compressed gas cylinders or pipelines that are pressurized and can even out the distribution hour by hour. Day by day, you can put hydrogen into a rock-lined cavern, if you will. And basically, this is a technology where they can drill a 10-foot diameter or a 20-foot diameter hole in the ground, and then line it with steel and cap it with valves to store hydrogen gas under pressure. And you could store enough hydrogen gas under 200 to 500 atmospheres pressure underground in this man-made system to power a city overnight. And then for the season-to-season storage, let's say your renewable energy is sufficient and more than sufficient during the summer, but can't meet demands during the winter, you can store hydrogen in underground caverns, salt caverns. And this is actually where the National Petroleum Reserve stores oil currently. You know, when a president has to boost his ratings to bring the cost of gasoline down, the president says, okay, we're going to release 1 million gallons of oil from our strategic reserve. Well, that strategic reserve is underground in caverns. And likewise, you can store hydrogen in those caverns. And this would be a large volume, admittedly at a lower pressure, but a large volume of hydrogen to even out the seasonality of your renewable energy. Okay, so hydrogen has the potential to be a good storage mechanism. Next slide. And this kind of brings us to what I would like to think of as a blue sky aspirational idea. And here in northern Arizona, we have a lot of wind and solar energy that's coming online. Stefan has kept track of this, and a total in northern Arizona of 1,424 megawatts of solar and wind electricity available to us. Here's the blue sky idea. The Babbitt Ranch solar and wind farm is just about 40 miles outside of Flagstaff along Highway 180 on the way up to the Grand Canyon. What if we were able to generate hydrogen at the Babbitt Ranch renewable energy facilities and transport it to Flagstaff through a dedicated hydrogen pipeline? We could then have one or more, well, let's start with one hydrogen fueling station at the junction, somewhere at the junction of I-40 and I-17, long-haul heavy-duty trucks powered by fuel cells could refill there and make it all the way to Los Angeles or all the way to Albuquerque. So that's just something to think about as a aspirational project. I want to just mention briefly that the federal government has just issued regulations that deal with the hydrogen, green hydrogen production tax credit. And these regulations are open for public comment, and comments are due to the federal government by February 26th. And the reason this is important, and I want to mention it to people, is that the fossil fuel industry has lobbied hard to keep their natural gas fossil fuel eligible for the green hydrogen production tax credit. And these rules, that the draft regulations that were just released about 2 weeks ago, have 3 pillars that are in there because of the federal government's desire to have green hydrogen be truly green. And these 3 elements are that the electricity for any green hydrogen, the electricity to run the electrolysis must be from newly built carbon-free sources. So the fossil fuel companies can't claim that they supported a wind farm 10 years ago, and now they're using that electricity to produce green hydrogen. To be eligible for the $3 per kilogram tax credit, it has to be from newly built carbon-free sources. Secondly, it must be physically deliverable to the electrolysis facility. And third, the electricity must be matched hour by hour with the power consumption. So they can't claim that they had carbon offsets in the Amazon rainforest, and therefore they're entitled to the $3 per kilo production tax credit. Anybody that wants to comment on these federal regulations can do so through the Federal Register up until February 26th. So we've covered a couple of the controversies that surround the how much water is going to be required. There's another controversy that is under consideration, and that is blending hydrogen with natural gas and put that through our existing pipeline system. There are a couple places where that's being tried on an experimental and an investigational basis. The concerns that people have raised is that it might be at more risk of fires and explosions than using pure natural gas. And finally, there's a controversy over where these pipelines, if there's going to be a new pipeline, is it going to go through a disadvantaged community, like many of our previous and existing infrastructure facilities have been placed in disadvantaged communities. So the federal government is placing a strong emphasis on social equity, on new hydrogen structures. They're insisting that these facilities be built with union or fair wage labor, and that it truly be green and not greenwashing. So let's open it up for questions and see if people want to explore anything further. While we're waiting for any questions, I want to just mention that the sponsor of these climate talks for everyone, the sponsor is the Northern Arizona Climate Change Alliance in conjunction with Fridays for the Future. And we're hoping through these talks to explore every avenue to mitigate our current climate crisis. And NASCA as an organization is trying to approach the problem on as broad a basis as we can. And the way we work is to create climate action teams. A good example here in Flagstaff is the pedestrian and bicycle climate action team. We have a group of about 10 activists that are working with city government to get improved bicycle and pedestrian pathways and to improve the traffic light structures so that it will be more favorable to pedestrians and cyclists. Another example of a climate action team is our Green Burial Climate Action Team. And that's a group of 4 or 5 individuals that are promoting green burials as opposed to fossil fuel cremation or standard cemetery burial that creates a lot of carbon footprint through the cement vault and the casket and the embalming and the maintenance of the cemetery. So those are 2 examples of climate action teams that we have going. We have, what, Stefan, 12 or 16 climate action teams at the current time.
There are quite a few, and they are all covering different elements of Flagstaff's carbon footprint. There are also NASCA groups in Sedona, Cottonwood, Verde Valley, and Prescott Quad Cities. And each of them are starting to form different climate action teams to address the carbon footprint in their communities. A question did come through, Dr. Spence, and that is, if the goals for hydrogen production for 2030, 2040, and 2050 are met, roughly what % of current fossil fuel energy would be replaced? Do we know that?
I am sure there are people in the Department of Energy and other research institutions who would be able to answer that question. I'm not knowledgeable enough. It's a good question, and I'm going to throw out an estimate, and that estimate would be 10%. That 10% of our fossil fuel consumption could be met by those amounts of hydrogen going into the future. But
Dr. Spence?
yes, go ahead.
Yeah, I think that was a great question from Jordan Dale, and it raises in my thinking another important point in all of this. So we've got the various ways of storing energy, and there are different applications for the different kinds of energy. And I think batteries can store for certain things. But for instance, if you're talking about long-haul freight trucks, if you had enough batteries to really carry that truck as far as it needs to go, it would have no more weight left for its payload, right? So that's a prime example where hydrogen becomes a really important alternative fuel. And so we don't necessarily need to cover all of our energy uses with hydrogen. But it's particularly well adapted to certain types of uses. So, and I don't know what the percentage breakdown is of where it would be best used.
Right. You're bringing up a good point there, and certainly if you can use electricity directly, as in a battery-powered electric car, that is more efficient than using the electricity through electrolysis to produce hydrogen to drive a fuel cell car. You might as well just use the electricity in the first go around and have a battery-powered vehicle. But Stefan, your point about a long-haul heavy-duty truck is a good one. The hydrogen fuel cell has a definite advantage in that it has less weight in the gross vehicle weight, less weight to move down the highway at 60 miles an hour or 70 miles an hour than the batteries, and the downtime for refueling. So a long haul truck, the trucker pulls into a truck stop, and while he or she is taking a shower and going to the bathroom and getting a meal, the truck is refueled with diesel. And in a matter of 10 or 15 minutes, the fuel tank is full and the truck is back on the road. A battery-powered long-haul heavy truck would have to spend 4 to 6 hours at a battery refueling stop. So the hydrogen is comparable to the diesel in terms of how long it takes to refuel your vehicle. So yeah, it is very much of a niche product, a niche energy mechanism. And another way to look at this is steel making. Currently, steel making is very carbon intensive. Steel contributes a lot to our global warming. Hydrogen has the ability to run a blast furnace as well as the fossil fuel, and better than electricity. You can get your blast furnace for steel making up to temperature with hydrogen mechanism more than electricity. So there are a lot of places where hydrogen is going to fit very nicely into our solving the global climate crisis.
Very good, Dr. Spence. Since we have a smaller group now, I would like to give everybody the opportunity to just unmute and ask your questions directly. If you could also put yourself on screen. So Dr. Spence and I have been feeling kind of like we're all by ourselves in a big room. So if y'all would please show yourself, join the conversation, raise your hand and I'll call on you. That way we won't have folks talking over each other. Donna. Oh, that was a hello. Okay. Any further questions? Yes, Jordan, go ahead and unmute.
So I'm a bit of a climate activist, and most of the climate activist community that I participate in, other activists put down hydrogen as being a false solution and one that tends to distract the world from doing the more serious work of eliminating the use of fossil fuels. So I tuned in because I wanted to hear more and understand more, and your presentation's been very helpful. But I'm just curious what you say. What is your reaction when you hear that objection to hydrogen from climate activists?
Okay, it certainly is a valid criticism. First of all, there can be some greenwashing, as we've discussed earlier in the hour. The fossil fuel companies are trying to promote their natural gas feedstock for making hydrogen by claiming they're going to capture all the carbon and sequester it forever. And we know that's yet to be proven technologically and economically. And as I just mentioned, if you can use the renewable electricity directly to keep the lights on, to run a heat pump, to power your vehicle, a battery electric vehicle, that is the best way to go. The place hydrogen fills a niche in our climate activism and solving the climate problem is in the storage capacity, either day to day, hour to hour, day-to-day or season-to-season storage, hydrogen is a really good way to store energy from when it's available to when it's needed. And finally, I would say the democratizing aspect of hydrogen. If we can get hydrogen technologies that are available around the world, developing countries won't have to go through creating an a nationwide electric transmission grid like our country has done. And we all know that a high voltage transmission line wastes 20–25% of the energy in just transporting the energy from one place to another. So if you can produce your hydrogen locally and use it locally to light your home, to cook your food, to cool your home, if that's what's needed in a hot climate, then the democratization aspect is really important in the developing world. And you know, what we've seen with cell phones, how they haven't had to build landlines. They've they've leapfrogged, if you will, directly to cell phones. We can, in our energy, we can leapfrog coal plants and electric transmission lines. And the beauty of that yellow hydrogen, if it can be developed and commercialized, you don't even have to generate electricity. You can use the sun's energy to split water into oxygen and hydrogen on a very localized basis. So I think a lot of the answer to the valid criticism is yet to be realized. You know, research over the next couple decades is going to show if the yellow hydrogen or the gold hydrogen can prove to be commercially available. But that's a good question.
Thank you.
Could I add? Again, there are certain applications where hydrogen is better than batteries and other ways to store that energy. And I think, I'm not sure if you completed that example with the forklifts, but one of the issues in a warehouse is all the exhaust. If you have gas powered, whereas it's a much cleaner exhaust, namely water, if you're running hydrogen fuel cell forklifts. So Barbara, you have your hand up. Go ahead. Unmute yourself.
While Barbara is unmuting, let me just say one thing that I forgot to mention is that the government, the federal government, has an aspirational goal of, they're calling it a hydrogen shot. And the title is patterned after the moonshot, where we put a man on the moon within a decade. The hydrogen shot is encapsulated by the 111. 1 kilogram. The aspiration is that within 1 decade, they will have 1 kilogram of hydrogen for under $1. The current price of hydrogen, if you buy it from a gas company, is between $5 and $7 a kilogram. So the federal government wants to be able to have hydrogen so cheap that within a decade, a kilogram will cost you $1. And, you know, that would be like $2 a gallon gasoline. So let's not hold our breath, but that's the goal. And a lot of research is being put into realizing it. Can we get Barbara's question over the verbal if we can't get it?
Barbara, are you there? Please unmute and ask your question. So I'm not sure if Barbara is with us still. Hopefully she will unmute and ask her question. But meanwhile, Beverly Hedden asks in the chat, how close is yellow hydrogen to production? And I think she may be referring to the artificial photosynthesis type of hydrogen.
Yeah, if you go to that website, sunhydrogen.com, it's tantalizing, but it's basically their corporate promotion of their patented technology. It remains to be seen if they can bring it to a commercial scale. It would be so exciting if they can, and only time will tell. Hydrogen, one other controversy that's going on in our country now is the liquefied natural gas terminals on the Gulf Coast or other ports. The natural gas, they want to take advantage of how the United States has a lot of natural gas available, and they want to export it. The feasible way to do that is to liquefy the natural gas and export it on LNG, liquefied natural gas tank ships. That's the current controversy as to how many of these export terminals do we need to build to continue to use fossil fuel natural gas around the world. And it's a false solution to controlling climate change, to continue to promote natural gas. But it is conceivable in the long run that hydrogen could be compressed or liquefied and transported around the world in tanker ships to where it's needed. And if you think about Australia and the Sahara Desert, or the Southwest United States, where we have abundant solar energy and wind energy, if you have a water source, and again, you have to pay attention, are you keeping a family in a remote area from having adequate and pure drinking water? But if you've got a water source and a source of sunlight, you can produce hydrogen, compress it, and ship it to areas of the world that don't have enough hydrogen. And Japan and Korea are two examples of two countries that don't have the natural resources to make their own hydrogen, and they're going to be looking to import it on large ships. So there's a use. If we get LNG port facilities, maybe they can be switched over in the future to hydrogen.
Dr. Spence, Barbara is struggling to find the unmute mechanism, but she put her question to the chat. So how real is the explosive power of hydrogen? How much of a danger is that?
Hydrogen is flammable if it's in a concentration between 4% and 96%. So if you have hydrogen, say in your garage, you have a leak from your fuel cell vehicle, as long as the percentage of hydrogen in the air is under 4%, it's not going to burn or explode. Above 4%, up to 96%, you've got an explosion hazard and it'll blow your garage apart. Above 96%, there's not enough oxygen to support the combustion. So it certainly is a risk factor, and that's one of the concerns people have about blending hydrogen into natural gas. The pipeline system, might it increase the risk of fires and explosions? So we need to be very cautious. And anytime you're using hydrogen as a fuel, you need to be aware that it's going to be very light and rise to the peak of any enclosed space. As opposed to gasoline, it's going to, if you have a gasoline leak, it's going to drip out on the floor and be an ignition source in that way. So it is a risk, but I want to give one more example of how we know how to make hydrogen safe. In any hydrogen fuel cell vehicle, there's going to be an inertial shutoff valve so that if the car is in a frontal collision, there's a valve that automatically closes upon impact. You know, the sudden deceleration will shut this valve and keep the hydrogen fuel in the tank and not let it leak out at the crash site. So an inertial shutoff valve is a part of every vehicle that's got hydrogen on board.
Well, if I could add too, consider this, we are already driving around little Molotov cocktails as it is, right? So the gas tanks in our combustion vehicles are not very well protected at all, and many times crashes end up in flames. The tanks on hydrogen vehicles are much more carefully designed and protected, and the chances of them going off is much lower than it is for our gasoline tanks.
Good, good.
Yeah, they're more protected, and it takes a high temperature to get the hydrogen to combust. So it's not quite as easy to ignite it as it is with gasoline.
Okay. Well, let's, I think we should wind it up. Stefan, if we can show our final slide, the cracked earth. I just want to thank everyone for being with us in this discussion. I appreciate the questions that people have brought up. I want to encourage people to stay tuned because there's a lot of federal money going into hydrogen research and development. And hydrogen, along with all of the other renewable energy developments that are going on, with all of the energy efficiency initiatives we have going, we have an opportunity to slow and eventually reverse the global warming that is creating the crisis for our world now. And this is an example of how we can be motivated to save the earth. And Stefan, can we show the progression over time of the Earth's temperature? The circular graph.
Oh, okay. So yeah, so hopefully we won't end up with the cracked and dried out Earth, and we'll maintain life as we know it. This is just to remind you all that NASCA is sponsoring this along with Fridays for Future US and Elders Climate Action and Prescott College and Flagstaff College are also co-sponsors. And we hope that you will join other parts of the series. All of these are recorded and they're part of a library now of presentations that are available on the nasca.org website. And if we don't do these things, here's what happens. Each turn around the circle is 1 year. You can see the months around the outside.
And that's where we are right now.
So let's not go there.
Thank you all for joining us. We'll look forward to the next Climate Talks for Everyone, which is coming up in a week, isn't it, Stefan?
Yes, and actually it's Katarina Meyer, who is the executive director of Fridays for Future US. She came to the United States to lead that organization here on this continent. So she is an amazing grassroots organizer and knows a lot about the whole climate movement. So it will be very interesting to hear her talk.
We'll reconvene then. Thank you, everybody, for attending.
Thank you all for coming.